Okay, so we were talking about uh, the preferences. I switched laptops and I went to another laptop. The example is the same, and now you have you. We were talking about unsupported blocks. So I
Mm-hmm.
was saying, if you have a block, let's say a lookup table, some configuration of lookup table that we didn't support,
Mm-hmm.
you may still be interested to run verification and consider that block as a black box.
Mm-hmm.
You just consider it anything.
Okay.
And you can have a counterexample that doesn't make sense because it's like the cosine problem.
Mm-hmm.
But at least you may prove things. It depends on your property.
Mm-hmm.
It's if you are trying to prove your properties, some output is between some range, maybe that block didn't impact that property.
Mm-hmm.
You see what I mean?
Okay.
So you may be interested to see what's happening anyway.
Uh-huh.
If Kaintu can do something with it,
Okay.
okay? And it's a sound abstraction because you are consider it as anything,
Mm-hmm.
okay? So it's
Okay.
not like it's not correct; it's correct abstraction. Um, so yeah, you can keep it active. So whenever there is some block that is not supported, verification will be done, will be carried out anyway. But Kukusim tells you if there is blocks that were abstracted. So it doesn't mean that we will run verification and tells you, hey, here's a counterexample. There is an HTML report tells you here is the block that were abstracted. If there is some,
Mm.
if there are nothing, if there are no blocks that were abstracted, we will not tell you anything. You see what I mean?
Hmm.
So it's not like we will hide this block from you. We will tell the user, hey, this block was abstracted, and that's very important. You don't wanna you don't wanna them debug the counterexample and say, oh, that doesn't make sense. How this block is generating this?
Hmm.
So they need to read the other reports generated by Kukusim. So they need to see the error messages and say, oh, this block was abstracted. That makes sense now.
Hmm.
You understand?
Okay.
So yeah, with counterexamples, you need to make sure that the first question that comes in mind, are there any blocks that were abstracted? Like, does my model contain any cosine or sine or skewer function or nonlinear function that Kokusim abstract? That's the first question that should come to
Mm-hmm.
your mind.
Okay.
You understand?
Yeah.
The last abstraction is abstract lookup tables for verification using breakpoints on table. You worked in that. You remember we did a
Mm-hmm.
contract for lookup tables.
Mm-hmm.
That's very important because what we notice is if we give the implementation of lookup table,
Mm-hmm.
let's say we give interpolation and we give extrapolation, we give the precise implementation of lookup table. For a given breakpoint x, we can give x1 and x2, we can give y. But if we use that implementation, we notice that it has a lot of nonlinearities. It has multiplication and division.
Mm.
It's interpolation.
Mm-hmm.
And we notice that it makes the verification harder. So we had a case study from our industrial partners that took like a day or more for that property to be to, and I think they didn't even like we didn't even have results after that day waiting. But
Okay.
if we use only abstraction of the lookup table, and what is the abstraction is that we only compute the cube of your breakpoints,
Mm-hmm.
the nodes, and you
Mm-hmm.
say if my inputs are inside this cube, then the output is inside that.
Mm-hmm.
What we call them uh,
Yeah. Polygon.
the polygon. You
Yeah.
just like it depends on how many dimensions we have.
Mm-hmm.
If you are inside that cube, then the output, we know what is the output. It's
Mm-hmm.
a sound abstraction, which means it's a correct abstraction.
Mm-hmm.
You
Mm-hmm.
only give what is the interval
Right. Right.
of the
Yeah.
output,
Bounds.
the
Yeah.
bounds.
Yeah.
And we notice that using this
Mm-hmm.
abstraction and without giving any implementation, that specific model finished in less than a second or two.
Oh wow.
So it's a
Okay.
huge difference.
Right.
So it's
Right.
like don't give kind to a lot of nonlinearities and a lot of things. So
Mm-hmm.
that's example that shows how abstraction is important.
Mm-hmm.
Because like a simple thing by giving information about the bounds can be sufficient to prove things.
Right.
Yeah, it depends on your property. So if your property is also proving things between bounds, then maybe that this abstraction is enough and make verification faster, and it's a sound abstraction, it's a correct abstraction. While this abstraction cannot be enough if your property is trying to prove that your output is equal to something, because you need the interpolation to be correct, and you need the implementation to prove that property. So it depends on the property. What are you trying to prove?
Right.
So that's why the user needs to understand all these preferences to have a very good use of CocoSim. He or the user should know what type abstraction needs to be activated or not, depend on the property he wants to prove. That's why preferences, the default preferences are good, but the user need to change them. They are not there to be sitting there. They need to be changed. And the verification results will vary differently. Like if you change preferences, we can see that there is some difference. Like waiting for a day for some property to finish versus seconds.
Yeah.
So you need to understand how CocoSim works to make a very good configuration that goes well with your model and with your property.
I see. Okay.
So now we finish with the abstraction preferences. Now we move to the verification backend. Here we only support kind2.
Okay.
But potentially in the future we will have other model checkers. So nothing to change by the user here. So since we're using kind2, there are some preferences related to kind2. And in the future, if we support another model checker, we will have preferences for that model checker. So kind2 is a model checker. Kind2 takes a looser input attached with some properties and do some magic, which is mathematical techniques, which that looser will be translated to a mathematical representation, and the property will be checked against that representation, that formal representation, and we will have the results back. Is it correct? Is it valid? Is it safe or not safe, or invalid, or falsified? And we have a counterexample, or kind2 will now be able to finish in a reasonable time with a reasonable memory.
So what's the properties? That's like a mathematical...
so your property in this example is that the output is always greater than 0. That's your property. Your model is that apps subsystem.
Okay.
Yeah. So your looser code will contain your apps subsystem as a looser node, the implementation.
A whole bunch of nodes, right?
Yeah, as much as you have in the Simic model.
Right.
And it will contain also the contract that tells him, hey, this subsystem this subsystem output should be always greater than 0.
Right.
So that's your property.
So so properties is some kind of mathematical statement.
Yeah, it's your property, it's your guarantee. It's a Boolean that should be always true all the time. It's a Boolean.
Okay.
If you see, this is always a Boolean. Is this greater than 0?
Right.
This can be anything. Integer, floats, anything. But this single or double, this should be always Boolean. And should hold all the time.
Okay.
That's what a property means in this context. You understand?
Yeah.
So we continue with the preferences, kind2 preferences. Compositional analysis. Let's do a video about it. This compositional analysis requires a video about it. It's very complex topic, and it's very important, and the user needs to understand. It's like the way with abstractions. You need to understand how things works, so you can choose to not or use this flag.
Okay.
The kind2 binary, you should keep it to local. We don't support Docker or kind2 web service. The SMT solver, you can choose.
What if solver SMT?
So SMT is the satisfiability modulo theories. That's the solver, the mathematical solver used by kind2. So kind2 is just doing like a translation from looser to an input language of that solver. It's like the same thing we are doing with CocoSimulink. We are translating Simulink to looser because looser is the input for kind2.
Right.
But kind2 itself is translating looser to something else.
Oh, okay.
And just calling a solver, which is a mathematical solver,
Mm-hmm.
we have Z3 and ES2, and then that solver can impact the results.
So those are the computational engine.
Yes.
So kind tool is just another translator to the input of this engine.
So Kind2 is a front end for this engine,
I see.
but also
Okay.
doing a lot of things to help the engines, like the same way we do for Simulink.
Mm-hmm.
They do like invariant generation. They do like things that can help the solver find the answer in a very reasonable time.
See.
Okay. So yeah, changing this Z3 or choosing one of them is important. So you can there is no like correct answer which one is the best.
Mm-hmm.
It's like choosing between Messi and Cristiano. For you is Messi.
Right?
Messi is the best for you. It's not Cristiano.
Right,
but in the soccer,
right.
we don't know which one is the best.
Right.
Each one has its techniques. Like one shoots from the far.
Right.
The same thing with the solvers.
See.
Like they are different, and we need to try both.
Right.
Use one. If it doesn't work, use the other.
I see.
That's how these preferences are very important.
Right.
And like this checks start assuming, it's just a flag. You don't need to understand it. What it doesn't mean, it's like if you understand it, you are going too technical, too deep into the solver, how the solver works.
Okay.
But you don't need, you just know that it's a flag that may impact the results. You may activate it, and if you can deactivate it to see if that's changed.
Okay.
You understand what I mean?
It's another option to play with. Okay.
No, you can play with. You can activate it or deactivate it to see if it does make a difference in the verification time. Right. But you don't need to understand what does it mean. That's my point.
Right.
Like you don't need to go read about Z3 and the ESs.
Yeah.
That's the same thing.
Okay.
The looser C binary is always local. We don't support Docker. I don't know why it's there because we were planning to, but keep it local. Verification timeout.
Yeah.
That makes you understand. It's like when you run Kind2, you have an option. You run it infinitely, and that's what there is an option called no timeout, which means I will wait until Kind2 finishes. It could be days, it could be weeks, it could be years.
Okay.
And that's not something that the user may want to do.
Right.
But I may want to do that because once I'm like after 3 days I'm like upset and doesn't want to wait anymore, I can just terminate Matlab or terminate the command by Control-C, and then we'll stop it.
Okay.
And you will just end anything. Right. But if you are interested to have a very specific timeout, then choose one of these options.
Okay.
This, just ignore them. This is related to this design error detection. We are only talking about proving properties here. So that design error detection it's an experimental feature that is not important. So verbose level is how much information does the user wants to see from Matlab, from Cuckoosim. So if there is something wrong in the Cuckoosim code, do you want the user says, oh, there is an error, we cannot do this. That's 0. Or maybe he can see the crash error, Matlab error. That's just a verbosity level. In any tool, you have a verbosity. Do you want to see error messages? Do you want to see like more levels of the reporting, or just a very simple reporting? For you, for example, as a developer, you want to go to 3 because you wanted to see the whole thing.
Right.
But for a user that doesn't want to see the Matlab crash. Reset preferences, maybe you played with them and you just want to go to the default, just click on reset and we'll go to the default. Okay. If you change, for example, abstractions, you change compile preferences and you don't remember what you did, just reset them.
Okay.
So we finished with the preferences. That was when we wanted to prove a property about the absolute value from video 1. We said, since this is an absolute value, it's picking the input if it's positive, or the negation of the input if it's negative. It should be always true that this output is always positive. And that's our property. One guarantee that says the output is always positive. Okay. So now, since we picked the right preferences, we said, and the important preference in this context is abstract integer machine types. We want to use Simulink machine types, int 8, not -infinity plus infinity.
Okay.
So if you choose abstract, it means that this int 8, this int 32, if we display the port data types, we'll tell you int 32. So if you use that, if you activate that abstraction, then it will, in my translation, I will consider that as integer, as natural number between minus infinity and infinity, and not as a machine type integer. You understand? You remember when I was explaining this abstraction?
Mm-hmm. Okay. Ah. Okay.
Okay. So in this case, I'm not activating this option. So integers are like this machine type integers are used as they are.
Mm-hmm.
So this is between is bounded.
Right.
Okay. So your property should be falsified.
Mm-hmm.
Why? Because if we pick the int mean of int 32, if we multiply -1 by it, we should have a negative number here.
Mm-hmm.
The same I explained to you with int 8. If you have -128,
Mm-hmm.
you do multiply by -1, will give you -128 because it overflows.
Mm-hmm.
You understand? And that's why, because we didn't do saturate on integer overflow. If we activate this option in the gain, it will tell him, hey, -1 multiply -128 is 128. And 128 is above 127. And that's my limit in for int 8. I'm giving the example with int 8, not int 32. And say, oh, that's, and the user asked me to saturate on integer overflow. So I will keep it 127. And your property will be correct.
Oh, okay.
But now I'm not activating saturate, which means 128 will be casted again to int 8, it will be back overflow to -128. And that's a negative number. So your property does not hold.
Right.
That's the counterexample that we are waiting. So let's even do something, maybe change this to int 8. So you can see that the counterexample will be -128, and they need to do something, change things also other places. Let me run this, see if it compiles. Okay, so for example, this should be int 8, and this should be int 8. Let's run again, see if it's okay. Okay, this should be inherit. Why he's inherit? Oh yeah, the switch should be inherit, and this should be inherit. I'm just solving the issue. I'm changing everything to int 8 so you can have a very nice counterexample. So the counterexample I'm waiting for is -128, which is the lowest number of int 8.
Okay.
The int mean. So now I can call kind proof properties. Since I picked the right preferences, always make sure that, so the preferences that I pick now that do not abstract integer machine types. So integer machine types will be treated as they are. Like if there is int 8, they will be treated as int 8. They will not be treated as -infinity plus infinity, as the set z, the natural numbers. Okay? So it's very fast because it's a very small example. Whenever things like quickly, we have the reports, and let me show you first the command video, the command window. Here you have Cocosim going through some pre-processing, some Lustre generation, and calling kind2. And if you ask verbose level to be high, you can even see the kind2 command run by Cocosim. So you can just copy this, and if you want to run your, and this is very important, for example, for large semantic models. You may be interested to see, hey, I just want to generate the Lustre code and I want to send it to the server, a very powerful server, where I can run kind2. So you can copy this command and use it for yourself. Here is the output of kind2, and it's finding the counterexample in less than a second. And it gives you a counterexample in XML format. The user does not need to know anything about this because we pass this counterexample and we bring the results back. So the results here, it says, okay, the running time of kind is 0 less than a second, and the total time, like including CocoSim generation, CocoSim pre-processing, and everything is 24 seconds. And it tells you, hey, the result is counterexample. This is your property was falsified, and the results are summarized in this JSON file. But you have also the report that is automatically generated. This HTML report, if you don't have it and you want to generate it again, you can just click here on the right in the context menu and go to CocoSim and do verification results. It will regenerate that again. So if you say, what does it say? This verification summary tells you your component is apps subsystem. You can notice that this is a pp file, which is a new file. We always copy the file and call it the original name underscore pp, so we don't break the original file. And we do the modification in this file. It tells you you have only one component that has been specified with the contract, and it tells you that contract is not valid. And it tells you this contract contains one property, guarantee output underscore greater than underscore, which is because we had sign greater than, we changed it to a word, equals 0. And if we go inside, we give you exactly the counterexample. And it tells you if you put the input as -128, that's what I was waiting for. I was waiting for the same example. And that's the only example that we have. Because if we have -127, the output is 127. That's the only case where the property does not hold. You understand? That's why if we have -128 multiplied by -1, we keep the same thing. Okay? And that's because of two things. Because these are integer, machine type integers. They are bounded and there is an overflow. If you have this specified with a saturate flag, then you shouldn't have a problem. You should always have this positive. Or if you consider CocoSim, tell CocoSim that, hey, abstract type integers, don't use machine type integers. Consider them as mathematical integers. Everything is between -1 and 1. Then this should be valid now. You understand?
Yeah.
You understand why it's valid? Because it's -1 multiplied in math. Then it's like we reason with math here. If we do that preference, activate a preference, versus we reason about machine type integers. So you see it's green, valid. It's green. You can see this like this, and you can nothing to see here. And let's go back to the counterexample. Let's say there is no saturation, and we want to use machine type integers. So I'm not sure if it does work, but sometimes it doesn't because it's not our code, it's our code. Let's see what we can do with the counterexample. It's good we pick this small example because it runs very fast and we have the results very fast. Usually when there's a counterexample, we have this in red and we have the reports, but what else we have? So let's see. Things are running in the back. We have a counterexample. We have the HTML report. So let's say what else we can do with the counterexample. If we go inside, we have a very detailed information for each guarantee. So if you have 4 guarantees here, you may have one is green, one is red, depending on which one is falsified, which one is correct. And if you click if you double click the block, you can have other things. This one is called display counterexample as signals. So you may be interested not in an HTML table. You may just like give me the inputs, display the inputs, and here you have counterexample input and output. -128. It's just a different format of the. Here is using Matlab or Matlab Tables. It's the same thing as the HTML one. Here is using the HTML version. You see, and here you can create a counterexample. You can create a hardness model. What does this mean? Creating hardness model? It's when you can replace the input by values, by a signal builder. If you remember the signal builder. So we put the input, we put -128 at the first time.
Okay.
And that will help you if you want. It's just like we remove the input, and we put, instead of the input, we put a signal builder with the counter example inside. With that test case, that falsify your requirement. Why that is useful? Because you can just run the simulation and you can understand, hey, what's the problem? Where is the... So the problem here is in 32, because we consider everything in 32, but let's switch int 8. The harness model does not work from the first time, but if you can check these things and then do this, you can notice that the output is minus 128, but it doesn't give me the intermediate results. And you can debug. You can imagine this is a very big example, and then this will be very useful. So you can figure out the intermediate signals, what are the values. If this doesn't work by clicking the signal, you just can put a display here or a scope if you want. You will see here, for example, that minus 1 of minus 128 was minus 128. Yeah, you see?
Yeah.
But let's debug it. Let's say, hey, saturate on integer overflow. Now it will be 128. 127. Because it's a 128 and everything above 127 is 127. You see?
Right.
So it depends. That's why it's very important to make sure that you are checking the right checkboxes here. You are doing the things as correctly. And that's cooking, where cooking is very useful, because it brings you counterexample. Oh, why I have this? Because the user just sees here -1. He doesn't see what's inside. He doesn't see if this one is activated or not. You see my point? It's like, that's why cooking can bring up a very useful way. So that's it. You can create a harness model, and that's very useful. Do you have questions?
No, go on.
You finished.
Okay.
We had a property, we run CocoSim, what else we can do? If you check compatibility, it's already done. When you do properties, it's done. In place, it's like it's first run the check compatibility and tells you, here, this is compatible. Test case generation and detection, design error detection are experimental features. The main feature is properties. So those are not very well tested, but proof properties is the main thing. If you want to generate code, if you want to generate to C, for example, to Lucer for verification of C code generation, you will find always that next to the Simulink model. So this is the Simulink model we played with. We played with contract absolute.slx. And let's remove this. So every time we have a file called absolute_pp, and that's the one we modifying. So we just copy this and we call it absolute_pp, and we do a lot of modifications inside. And you can see always there's a folder called CocoSim output, and that CocoSim output contains a folder for each model you run. So in this case, all this set of blocks, we only run absolute_pp. So inside you have all the files are used by kind2. So for example, this absolute_pp.kind2.loose is the Lucer file of the Simulink model. We call it .kind2 because we use kind2. If you use for generates Lucer for code generation, you will see the name .lucerc.loose, because lucerc is the one used for C code generation. You understand?
Yeah.
So if you do verification, you will see your name of the model _pp.kind2.loose. This one contains some important some variables that can be used later on by CocoSim if you rerun things you don't care about. These are your counter example, the results from kind2 in a XML format, so you can keep them or send them to as a report to other people. But so these are the traceability, because the Lucer file contains other names than the Simulink file. So if you open the Lucer, you will see this called absolute underscore pp, and it's calling some subsystem called apps underscore 7 underscore 00. So this apps 7 underscore 00 is the subsystem apps. And who is telling you this? There is a traceability file. This traceability file is keeping track of all of telling you the node name called apps underscore. This is the original Simulink path. So this is just a traceability of here is the node, here is the subsystem associated to. So because the names used in Lucid are not the same used in Simulink. So these are the traceability file used by us, by CocoSim, to bring the results back to the user. But these are very are only important for the developers. So these are verification results in a different dates and different times. You notice like 6 October, 21 October, 21st October, 30 September at different times. We use the timestamp so we can keep track of the results. So if the user run verification, we give them a report. Hey, here's the property and here is the country example. The answer of the property is country falsified, and here's the country example. You understand? In a JSON format. So even you want the XML format or you want the JSON format. Which is this one is better because this is the output of CocoSim and it's using the Simulink names instead of Lucid. So it's doing the work for you. You don't need to worry about it. So these are different because we run the model many times. There is a mapping, it's the same. And yeah, that's it.
Okay.
If you want to go over another example, let me know, or maybe you want to go over compositional verification.
Yeah, let's do that.
Okay, so let's finish this video and do composition in a separate video.